This is the topic I will introduce this time, a multi-resource scheduling scheme of Kubernetes for IoT. First, I will introduce the motivation of this paper with the rapid development of IoT data applications. Many use cases require sensor data collection, device control, and remote monitoring. These applications often have high real-time requirements. However, existing resource scheduling methods face the following challenges: diverse resource requirements. Kubernetes focuses on CPU and memory, but IoT needs diverse resources like bandwidth and storage, which the default method fails to address. Insufficient resource balancing. Existing methods overload some nodes, while underutilizing others, reducing overall system efficiency. Neglect of latency requirements. IoT requires low latency, but current methods ignore geographic proximity and latency control. Limitations of existing methods. Current strategies overlook task-specific needs and system dynamics, relying on simplistic algorithms. Next, I will introduce the architecture of Kubernetes. Kubernetes consists of master node and worker nodes. The master node is responsible for managing the entire Kubernetes cluster, including scheduling schedulers, monitoring, and resource management. It mainly includes etcd, which is a distributed key value data store used to save the configuration information and state data of the cluster. QQB scheduler, which is responsible for assigning pods to appropriate worker nodes based on scheduling policies and resource availability. Kube Observer, which serves as the main interface between users and the Kubernetes cluster, processing REST API requests and updating the cluster state. Kube Controller, which executes control loops to ensure the cluster's desired state is consistent with its design. The worker nodes are the machines that run application workloads and are responsible for executing pods. They mainly include a Kube proxy, which handles network connections between nodes, ensuring smooth communication between services and pods. A kubelet, which is the core agent running on each node, responsible for creating and maintaining the desired state of pods based on instructions. Docker, which runs containerized applications such as app-A and app-B, as shown in the diagram. A pod is the smallest deployable unit in Kubernetes, and each pod can contain one or more containers. Users or external systems interact with Kubernetes through Observer to submit workload requests or manage cluster resources. Next, I will introduce the Kubernetes default scheduling process. First, the user submits a request to create a pod. Then app server processes the user request and etc stores the pod data. Next, the scheduler checks the new pod through the watch mechanism of the API server and tries to bind the node to the pod. After that, the filter traverses all nodes in the cluster and fills out a list of nodes that meet the requirements according to specific pre-selection strategies. If no node meets the pre-selected policy, rules the pod will be suspended until the required node appears in the cluster. Based on the preselected node list, the scheduler will score and sort the candidate nodes according to the preferred strategy. To obtain the optimal node, the scheduler then selects the host with the highest score, performs the binding operation, and stores the result in its side. Finally, the kubelet executes the pod creation operation based on the scheduling result. Now let me introduce the main scheduling strategies in Kubernetes. The default Kubernetes scheduling strategies can be divided into two categories. First is the strategy that focuses on node resource richness and resource balance. This strategy evaluates the resource status of individual nodes and aims to achieve a more balanced resource allocation. However, this approach has a limitation as it neglects the specific requirements of individual pods and the overall system performance. The second is the optimization of global system performance. This strategy emphasizes the resource utilization efficiency of a tile, entire cluster, by considering the performance of the system as a whole. But the limitation of this strategy is that it may cause certain nodes to become overloaded, which can negatively affect system stability. These two strategies provide a basic framework for scheduling, but they have their limitations in meeting specific demands or optimizing overall performance in complex scenarios. Let me introduce the delay-based node filtering process. In IoT scenarios, IoT systems require extremely low latency and fast response to maintain their operations efficiently. However, the default Kubernetes scheduling strategy does not consider the physical location of pods. This can result in high communication delays between nodes and the II to working environment if all data storage, processing, and responses rely entirely on remote cloud servers. The system's latency will become unacceptably high for IO applications. To address this issue, they conducted an experimental analysis of node response delays using 102 servers across China. They selected 3 specific test nodes for the analysis. The experiment produced a figure 2. First, figure 2. The response delay heat map. This figure visualizes the delays between the 102 servers and the 3 test nodes. Darker colors represent higher delays, while lighter colors indicate lower delays. It is observed that the node Nj achieves the lowest delay at just 13 milliseconds counts corresponding to the server. In Nanjing, this shows that the geographic location of nodes significantly affects delay. Next, figure 3, the response delay aggregation diagram. This figure aggregates the delay data for the 102 servers and shows that delays within the same administrative region are highly consistent and clustered. The data indicates that nodes in the same region tend to have similar delay characteristics, making them suitable for region-based node grouping and management. Figure 4 illustrates the default node filtering scheme in Kubernetes. In this scheme, node selection is performed without considering delay requirements. As a result, the chosen nodes might meet the low latency demands of IoT applications. This limitation highlights the need for enhanced filtering mechanisms. Next, figure 5 presents the proposed node filtering scheme designed to address these challenges. This scheme introduces a hierarchical structure based on administrative regions to improve node filtering. Nodes are grouped according to their geographic location and delay requirements. A delay-based scoring mechanism is then applied to select the optimal node. The key features of this improved schema: first, it ensures low latency by prioritizing geographically closer nodes. Second, it facilitates localized resource utilization, which is highly suitable for IoT environments. Now I will explain the scoring strategy based on pod resource requirements in the MRS scheme. First, the traditional approach often categorizes jobs into broad types, such as data-intensive jobs, real-time jobs, or others. However, in complex ICA scenarios, this approach is insufficient as the resource demands of pods vary significantly. To address this, the MRS strategy evaluates the specific resource requirements of each pod instead of simply categorizing jobs. Each node is scored based on how well it satisfies the pod's resource demands. Now let us look at how resource weights are calculated. First, the weight ratios of resource demands are calculated based on the pod's requirements relative to standard reference values as shown in Formula 9. These ratios account for the pod's demands for CPU memory, network bandwidth, and disk in comparison to predefined standards. Next, these weights are normalized to ensure they sum to 1. This normalization process is outlined in formulas 10 and 11, producing a set of normalized coefficients for each resource type. The final weights are represented as a weight vector W, which combines the normalized values for CPU, memory, network, and disk. After calculating the weights, the next step is to evaluate the available resources in each node. For this, the remaining resources in a node are normalized as shown in Formula 13 by dividing the available resource amounts by the total capacities. In the node, this step generates a resource vector P, which represents the proportion of remaining resources for each type. Finally, the node score is calculated using the dot product of the weight vector W and the resource vector P, as seen in Formula 14. This score indicates how well the node meets the pod-specific resource demands. Next, I will explain the scoring strategy based on system performance in the MRS scheme. This part of the scoring process focuses on evaluating the overall performance of the system and ensuring balanced resource allocation across the cluster. First, the system resource weight is calculated to resource utilization in the entire cluster, as shown in Formula 15. The resource weight is determined based on the average total occupancy of CPU, memory, network, bandwidth, and disk in the cluster. These values are then compared to the total available resources of the respective types in the system. It is important for you to know that the occupancy values used here are not the instantaneous usage, but rather an exponentially weighted moving average as explained in Formula 16. For example, the CPU usage is calculated using both historical and current usage values to smooth fluctuations and avoid overreacting to temporary spikes. Next, the calculated coefficients are normalized as described in Formula 17. This ensures that all resource weights are proportionally balanced. The normalized coefficients for each resource type are represented by a vector beta as shown in formulas 18 and 19. the remaining resources in each node are evaluated using the same normalization process as described earlier in Formula 20. This creates a normalized resource vector for each node. Finally, the system performance score for each node is calculated using Formula 20. This score is derived by analyzing the balance between resource utilization and availability. The goal is to reduce the weight of resources with higher utilization rates and prioritize more balanced allocation across the system. In this final step, the MRS scheme combines the scores from pod, resource requirements, and system performance to calculate a comprehensive score for each node as shown in Formula 22. The score is calculated as score equals sigma times score subpod plus 1 minus sigma times score subsystem. Here score subpod reflects the pod's resource demands, score subsystem reflects the system's overall performance, and will balance by adjusting sigma. The balance between pod specific needs and the system efficiency can be tailored to the scenario. This ensures optimal scheduling for IoT environments. Now, let me explain the experiment conducted to evaluate the proposed container scheduling algorithm. The experiment is based on the open source simulation frameworks CloudSim and NodeSim. CloudSim is used for testing cluster resource imbalance, while a NodeSim focuses on delay experiments. The simulation framework represents a Kubernetes edge cloud with 50 nodes to reflect a real-world diversity. The experiment considers types of resource demands, each corresponding to a pod type. These types focus on CPU usage, memory usage, network bandwidth usage, storage usage, and a balanced resource distribution. Evaluation metrics. 3 main metrics are used to assess the experimental results. Response delay. This measures the time required to transmit a message or pump the IO production environment to the scheduling work node. Cluster resource imbalance. This metric evaluates the balance of resource utilization across the cluster. It is defined by the standard deviation of resource utilization for all nodes, as shown in formulas 23, 24, and 25a. Lower imbalance value indicates better balanced resource usage, improving clusters' overall efficiency. Reasonable rate of scheduling. This metric checks whether the scheduling decisions avoid assigning pods to nodes where resources have reached their upper limit. The reasonable scheduling rate is the ratio of reasonable scheduling actions to a total scheduling requests with an ideal value of 1. First, We compared the response delays after scheduling using two strategies as shown in Figure 6. The proposed region label scheduling assigns region labels and delay requirements to pods, filtering out nodes that exceed the delay thresholds. Only nodes meeting the delay standard are considered for scheduling. The default scheduling method does not consider IO-specific delay requirements and uses a basic filtering approach. From Figure 6, we see that the proposed region label scheduling significantly reduces response delay compared to the default method. This improvement is due to the effective selection of nodes optimized for IO environments. Next, let's examine the resource scheduling performance as shown in Table. 3 strategies were evaluated: the default Kubernetes scheduling method DRS, the ant colony algorithm, which is an effective but complex scheduling method, the proposed MRS scheduling strategy. Two key metrics were used. Class source imbalance reflects the even distribution of resources in the cluster. Reasonable scheduling rate, which measures the proportion of successful scheduling requests for smaller workloads. With 2,000 pods, the differences among the methods are minimal. However, as the workload grows to 10,000 pods demonstrates a significant advantages. It maintains a high reasonable scheduling rate of 1, similar to the ant colony algorithm, but achieves lower complexity and better resource balance than the default method. Finally, Figure 7 shows the changes in cluster resource imbalance as the number of scheduled pods increases. For workloads with less than 5,000 L pods, the imbalance levels of MRS and DRS are comparable. For workloads above 10,000 pods, the MRS method shows better resource balance, reducing the likelihood of overloading specific resources. By dynamically adjusting the weights of resources such as CPU, memory, bandwidth, and storage, MRS adapts more effectively under high load scenarios. This makes it superior to the static weights used in the default Kubernetes method. Now let me summarize the key conclusions of this study. First, MRS effectively reduces response delays by using region labels and delay requirements. This makes it particularly suitable for IOC specific needs where low latency is critical. Second, MRS achieves better resource balance compared to the default Kubernetes scheduling method, especially under high load conditions. This ensures a more even utilization of resources across the cluster. Third, MRS maintains a high reasonable scheduling rate while optimizing resource allocation. Its lower complexity compared to traditional methods further enhances its efficiency. Finally, MRS considers multiple resource types, including CPU, memory, bandwidth, and storage. This leads to more efficient and balanced scheduling for complex workloads.